So sampling distributions is what we're taking a look at. This is section 3.1. So remember, a distribution is just a graph, a histogram. And what the sampling means is we're looking at many, many, many different samples. So the two types we're going to focus on, the book does a few more, but we're going to look at sample means and sample proportions. So the kind of examples that we're going to explore here for sampling distributions is we could have a distribution of sample means. So maybe I have n equals 100 as my sample size, people, and I want to know what's average body temperature. And so I just take lots and lots of samples, every one of them size 100, and take a look at the graph of the averages. So we only graph the averages. Only graph average of many samples, each of size 100. And if I did that, that would be a sampling distribution. Another example would be a proportion. So that's like what percent of people or things have some property. So I could have a distribution many sample proportions. And one that comes to mind is I was shopping this weekend and looking for some snacks, and this one can of mixed nuts said they had less than 50% peanuts. And I don't mind peanuts, but I like other nuts too. And I was like, oh, great, cool, let's get it. So in that case, I would look at the proportion of peanuts in the container. So I might do n equals, did they lie? I did collect some data on that, and I'll show you. And so then we'll have to figure out, did they lie or tell the truth? So n equals 50 nuts, right? And I want to know what's the proportion of peanuts. Is it less than 50 like they claim? Proportion of peanuts. And the sampling distribution here would be to only graph the proportion of peanuts from samples each of size 50. And see what happens. So that would be a sampling distribution. And we're going to do this a little bit in practice, but mostly this is like a theoretical idea, and we simulate it with a computer, because I don't want to go and get many cans of mixed nuts and 1,000 times grab 50 nuts and count how many peanuts are there, right? I'm not going to do that. But I'm curious about it. So back to StatKey for a minute here. Let's see. And here's the StatKey homepage. If anybody missed this, I'll get in the chat. I'm going to look for sampling distribution of a proportion. I think they might have had the mixed nuts here. Oh, they're college graduates, coin flips. All right, where did they put the mixed nuts? Proportion here. There we go, mixed nuts. All right, so I'm on the confidence interval proportion page. I'll put that in the chat if you want to go here, test it out. And here they have actual data. So somebody went and grabbed a can of mixed nuts. They grabbed 100 nuts out of the container. They counted and they found 52 peanuts out of the 100 nuts. So their proportion is 0.52. Now, what we're going to do is we're just going to replicate that by generating more samples. So I don't know if their container was the 50% less container. That's a good question. So I'm not sure if these guys lied, but maybe. So if I generate one sample, what this computer's doing is there's 100, let's say, cards, like a deck of cards, and the card has, it's either says it's a peanut or it's not a peanut. And so we shuffle the deck and we redraw one card at a time, looking at it, writing it down, put it back in the deck. So when we look at it, we either say, okay, it's a peanut or not. So they did that to the deck of cards, and this time when they redrew from the deck of cards, they found 58 of the cards said peanuts and the other 42 did not, sample size 100. And if we do this over and over again, like I do another one, next time they found 55 peanuts out of 100. Next time they found 45 peanuts out of 100. Right? So there's going to be variability in the sampling from the can of nuts. Now this is assuming that there's 52% peanuts in the can, is what I'm assuming up here. And as I keep generating more samples, I'm going to see those points jump around on either side of 52. Some of them might even come out to 52. I didn't get one yet. 51, 53, 51, 49. So they're all different. So instead of doing one at a time, I'm going to start doing thousands. So right now, what just happened? 1,042 samples. Each sample is 100 nuts. And here we're graphing the percent of peanuts. So this point right here says there were 55% peanuts. This point over here says there were 47% peanuts. This point out here said there were 73% peanuts. Oh my gosh. And maybe that was at the bottom of the can, all the peanuts sunk to the bottom. Maybe this was at the top of the can, all the peanuts are at the bottom. There were only 36% peanuts. It wasn't a well-shaken can, right? But the thing to note here is the more samples I do, and so right now I've done 4,000 samples. Each sample had 100 nuts in it. Look at what the average percent of peanuts is. 51.9%. The original sample had 52%. Notice how that's pretty close. And this is the idea of a sampling distribution. If you do lots and lots of samples, then what you should expect is that if you average all of those samples, what number's right in the middle, it should be pretty close to what the population was or is. Problem is we never know what the population is, but this idea helps us get there. And what we're going to try and do is just off one sample, can we estimate the population? And then it's always an estimate, so how far are we off, right? Where's the real population? That's the problem. We don't really know. So let's look at a different example. So go back here. We are going to look at percent of college graduates, I think. Let's see, stat key, sampling distribution, proportion. Yeah. All right, new page. So question, what percent of adults in the US are college graduates? And this data, down somewhere. I think it is, oh, I didn't write it down. Okay. 2016 is what I want to guess. Hang on. I can't find the dates. Okay, well, it's recent. I'll look it up later. So what percent of adults in the US are college graduates? Question mark. So a study was done within the last few years, and they found that 27.5% of US adults had a college degree. So we're going to say this is the population proportion. So if I have a P with no hat on it, we consider that the population proportion. And that's believed to be 27.5%. Often they're stated as decimals, so 0.275 is the population proportion here. So this is an example from the book. Let me drag it over here and look at it with you. So this is from, okay, US Census. So this must have been from 2010 data because the 2020 census wasn't out yet. With a bachelor's degree or higher. So US Census claims, and we'll talk about what census means here too, 27.5% of US adults who are at least 25 years of age. Okay, so that's our definition of an adult here, which makes sense. It takes a few years to get a college degree, a bachelor's degree or higher. Now, what if we took a random sample of size 200? So let's do that. So back to stat key. And sample size right now is set to 200. And I'm going to grab one sample. So I grab one sample, and in my sample, 60 out of 200 people had a college degree, 25 or over. So let's make a note of that. So in a sample size n equals 200, p hat is 30%, so 0.3, 30% have a college degree. That would be, right, so p hat could be a percent, decimal, or fraction. So if I look back at stat key, they give me the decimal version and they give me the fraction. Count 60 out of the sample size 200 here. And that's the 30% here, and they give me some extra zeros, which I don't really need. So p hat is x, the count, over n, the sample size, and in this case, that is 60 over 200. So that's certainly one way I can state it. P hat is 60 out of 200. 60 out of 200 of the people in my sample had a college degree. Could state it as a decimal, 0.3, or it could state it as a percent, 30%. And depending on the situation, we'll jump around with that. Usually in a computer calculation kind of thing, decimals are used more often than anything else. But sometimes we do have to have counts also. Now, there's going to be sampling variability in that every sample is going to be different, right? So if I generate another sample, something different is going to happen. So in this one, 52 out of 200, or 26% of the people in the sample had a college degree. Right. So this, we're making believe we have all of the census data, which means information from every possible adult 25 or over in the US in 2010 is the population. And from all of those adults, we randomly grab 200 of them. We think it's a good sample. And we say it looks like about 26% of the population, adults 25 and over, have a college degree in the US. But again, every time we do a small sample, and a small sample could be 1,000, compared to the US population, 1,000 is pretty small, but oops. Here we're just doing 200. And notice every time I do it, whoa, that was a really low one. Notice the whole graph shift when I get that one. What does this one say? 18%. If I look over here. Now I'm just going to generate 100 of them. So every one of these is an estimate for the population. Now, just some reminders about terminology and what we're doing here. Right? We've got this population out there. And there's all these things about the population, like the average age and the average people with college degrees and all these other things, right? So we're trying to find a parameter in the population. In this case, the parameter I'm looking for is P, the proportion of people with college degrees. If I had everybody in the population, so if I tried to sample every person in the population, that's no longer a sample, right? A sample is part of the population, not the whole thing. But if I got every person in the population, that's called a census. So literally, census means go talk to every single person, get information about every single person in this region. And in this case, it's the US Census, which means they're trying to get in contact with every single person in the United States. So I don't know if you remember back in 2019, 2020, there were signs up in every town saying, hey, come work for the census, help us collect data. You get paid. And I know a bunch of people who did that part-time, kind of going around door to door. Do they still miss people? Yeah, there's some people that just refuse to participate. But it's pretty close to the entire population, like 99.9% is my guess of what they get. But again, they do miss some people, but the attempt is to get every single person. And so that's what a census is. So in this case, the information that I started with, let's go back here. This number right here, the 27.5%, that is a parameter because it's a value that represents the entire population. So this right here is a parameter. Whereas when I just grabbed the 200 people right here, this 30% right here, that is a statistic. So a statistic is a calculation based on a sample. A parameter is a calculation based on the whole population. And we got to distinguish those. And generally what we do, since it's so hard to get the whole population, we really don't know that most of the time. And so what we would say is that p hat, that 30%, the 0.3, is our best estimate. For the population. So in this case, it's our best guess that 30% of US adults 25 or older have a bachelor's degree or higher, is what we're saying right here. Now, normally we don't know the actual population, so this gives us an idea to check. Now, whenever I estimate like this, there is an error. And I can kind of estimate that margin of error here in stat key. So if you're not on this page with me, I'm going to reshare it. You ought to try this too, to see that what you get is going to be similar to mine, but different. So I'm going to reset my plot here. And I'm just going to grab 100 for now. When we try to estimate the error in a sample estimate of a population, so maybe we're estimating the average of something or the proportion or percent of something, there's always going to be some error. And the usual way to guess at that error is to use that 95% rule that we talked about a few weeks ago. So we're going to try that in a sec here. So estimating error, usually called the margin of error. We're going to use the 95% rule, which was also known as the 2 standard deviation rule. So picture of that as a reminder, we have this distribution of data, and let's pretend it's a symmetric bell shape. Right in the middle of that symmetric bell shape is going to be the average. Let's say it's a mean, in this case, X bar. Now, standard deviation measures the spread of the data on average from the mean. And so let's say that's 1, 2, 3 standard deviations to the right. And then let's go out 1, 2, 3 standard deviations to the left. So this one right here would be X bar plus 2 standard deviations. And this one over here, I have to go back 1, 2 standard deviations. So that number right there would be X bar minus 2 standard deviations. And what happens is that most of the time, if you look at all the individuals that live in the middle here, about 95% of the data is going to live in this region right here, within 2 standard deviations of the mean. And so which is most of the data. So to estimate how far off our guess, our sample data is from the population, we say that the margin of error, that distance that could be off on either side, that's that 2 standard deviation. So we're going to use this range right here, 2 times the standard deviation, to be the margin of error. And what this builds is, instead of X bar being the estimate, a single number being the estimate, we now have this kind of window that we think the actual value is. And so StatKey can help me do that. We'll do more with this in just a minute. So what I want to do next is, so I'm at this sampling distribution for proportion page in StatKey using the college graduate data, n equals 200, and I just went and made 100 samples, each of size 200, from a population where 27.5% of people have a college degree. And there's a lot of variation that happens in each sample. But the center of the distribution, in this case, it's 27.9% down here, right? A little higher than the actual population, but on average, close compared to the range I have here. I'm going to switch from the data tables tab to the confidence interval tab. And what this does is it uses that 95% rule and says, okay, for this particular one right here, that is our estimate, 30% for the population, but we could be off. So then the computer calculates that 2 standard deviation rule and says, okay, the actual error is somewhere this far to the right and that's far to the left. And they're graphing these up here. So when I point to one of these, it says, okay, you notice over here the point that just lit up in the middle. I switch to a different one, a different point lights up. So sometimes these interval estimates I make here, the center with the margin of error, hit this black line. The black line right here is the actual population, 27.5%. And sometimes my sample is close enough to that, so its green bar overlaps the black bar, but sometimes, like this one right there is 20%, which is way over here, we missed. So the margin of error for this one doesn't catch the actual population. So notice how many missed here. It says 92 out of 100 captured the actual population, and the other 8 missed it. So I was aiming for 95% catch, but I ended up with 92. And it's always going to be a little bit different. So if I reset, do another 100, this time I got 90% of the time, my samples were close enough to the actual population using the 95% rule. And so we're going to learn how to make these lines, these intervals that are popping up here. That's what we're going to work on next. Before we do that, let's have a brief, see what you guys remember from what we just went over. So pause this.